Sometimes the universe hides its biggest secrets in the most unexpected places. Today, we're going to track down one of the most famous numbers in all of mathematics, pi. But we're going to find it somewhere you would never, ever think to look.
Just look at this thing. It is a beast of a formula. It seems totally random, right? It's just built out of the imaginary number I, the number 7, and a few basic operations. And yet somehow, when you crunch all those numbers, you get pi. I mean, how on earth is that even possible?
So that's the big question. Is this some deep, fundamental connection, like a hidden law of the cosmos? Or is it something else? Well, that's the mystery we're going to unravel right now. All right, to figure this out, we have to start with the most intimidating part of the whole equation, that crazy stack of i's. It's actually called a tower of power, and the trick to solving it is you have to start at the top and work your way down. So our very first step is to figure out what I raised to the power of I is. Now, to do this, we're going to pull out a really powerful tool from the Math Toolkit, which lets us write I in a different way, as e raised to the power of I times pi over 2. And here's where it gets wild. When you do the math, something totally unexpected happens. You take an imaginary number, raise it to an imaginary power, and you get a completely real number, about 0.2078. This is our first clue that maybe this formula isn't as random as it looks. Okay, so let's keep building this. For our next step, we take that real number we just found, and that becomes the new exponent for I. So now we're calculating I to the power of about 0.2078. This time, we don't get a simple real number. Nope. We get a complex number, one that has both a real part and an imaginary part. You can think of it like a point on a map, and this specific point lands right on the edge of what's called the unit circle in math. And now for the grand finale of the tower. We take that complex number we just got, and we use that as the exponent for our very last I. Yeah, we're raising an imaginary number to a complex power. And the result is the big prize from climbing this tower, a final, unique, complex number. It's not on the unit circle this time. It has its own special spot in the complex plane. To make things easy, let's just call this final number W. So let's do a quick recap of that wild ride. We started with I to the I, which amazingly gave us a real number. We used that number as an exponent to get a complex number on the unit circle, and then we used that as an exponent to land on our final complex number, W. Phew! Okay, deep breath. The hardest part is officially over. We've got our number W. Now we can head back to the original formula and start plugging in the real and imaginary parts of W to see what happens next. The formula tells us to do something super specific here. We need to take the imaginary part of our number W and divide it by 7 times the real part of W. This is going to create a very particular ratio. So that ratio ends up being this tiny positive number, a little over 0.01. And the next instruction from our formula is to take the fourth root of that number. This is a really key step because it's going to scale our value up quite a bit. And taking that fourth root gives us our next critical piece of the puzzle, the number 1.1447, and so on. This number right here, this is the magic ingredient we need for the very last step. All right, this is it, the moment of truth. We have cracked the tower of power. We calculated the ratio. We took the fourth root. There is only one final operation left to see if this whole bizarre journey actually leads anywhere. The formula asks us to do one last thing. Take the number e, the base of the natural logarithm, and raise it to the power of that number we just found. So what do we get when we take e to the power of 1.1447? There it is. 3.14159261, it's pi. I mean, wow. Against all odds, this completely chaotic-looking formula, built from imaginary numbers, spits out one of the most fundamental constants in the entire universe. And it's not just kinda close. Look at this. When you put our results side by side with the actual value of pi, it is dead on for 7 decimal places. That is an unbelievably close approximation. So what is really going on here? And that brings us right back to our original question. Is this some kind of secret code of the universe? Well, it turns out the answer is no. It's not a conspiracy, it's a coincidence. But it's a really, really beautiful one. This is what mathematicians call a numerological coincidence. It's not a fundamental law of nature like E equals mc squared. It's more like a surprising result that just happens to pop up when the specific properties of the numbers and functions you're using line up in just the right way. So what are the key ingredients that make this work? Well, it all starts with the powers of I, which don't behave randomly at all. They move in a really structured, cyclical way. Then, by taking these careful ratios of the real and imaginary parts, you can basically engineer very specific, tiny values. And finally, the exponential function acts like the perfect magnifying glass, taking that carefully crafted small number and glowing it up into something big and famous, like pi. So, really, you should think of this formula as a brilliant piece of mathematical engineering. Someone, somewhere, figured out that if you stack i's in just the right way, divide by 7, and take the fourth root, you could build an exponent that when you feed it to e, gets you ridiculously close to pi. It's not revealing a secret law, it's just cleverly exploiting the way these numbers behave. So what's the big takeaway from all this? Well, even if it's not some secret message from the universe, it shows us something truly amazing about math itself. It's a system that's so rich, so interconnected that you can find these completely unexpected, beautiful patterns that honestly, they just look like magic. This whole thing proves that even when you're playing in the most abstract corners of mathematics, using numbers that are literally called imaginary, you can still find these incredible echoes of the fundamental constants that describe our physical world. And it just leaves you wondering, what other perfect alignments are out there, hiding in plain sight, just waiting for someone to find them?